So now you've learned the basic concepts of modular arithmetic. You've learned the basic properties such as additive and multiplicative and some exponential properties. And now we can look at some basic examples. For example, this problem, we need to find the two primes p and q such that p plus q is equal to p minus 2q to the power of 3. And we think that we may solve this problem using modular arithmetic, right? And the difficulty in solving those problem is choosing which number we want to mod. We want to mod q or mod p or mod anything else. And we can have some try, right? If we mod p, the left hand side becomes q, and q is congruent to the right hand side becomes minus q to the power of 3. And this doesn't give us any very meaningful thing, right? It gives us q cubed plus q is equals to q plus q times q squared plus 1, and this is divisible by p, and we have p is divisible by q squared plus 1, and we don't know how to proceed, so we try modular q, and similarly we got p is congruent to p cubed mod q, and we get if we expand a little bit, do some algebraic manipulation, we get this equation, and this is congruent to 0, which means q is divisible by either p minus plus 1 or p minus 1. We don't know how to proceed. Oh, by the way, because we've noticed that p and q, the GCD of p and q should be 1. They are co-prime, because if they are not co-prime, it means that p equals q because they are both primes, right? If p equals q, we can check 2p is 0 if we substitute into this equation, and this is impossible. So p cannot equal to q, and so p and q are co-prime. Yeah, and that's how we get rid of p and get rid of q in this two modular arithmetic. But although we have some kind of although we have some kind of divisibility thing, but it cannot give us anything meaningful. So we may look at other choice of modular. We may try mod p plus q, and because we've got p plus q is equals to p minus q cubed, and as a result, p plus q is p minus q cubed is divisible by p plus q, and p minus q cubed is congruent to p minus q, and add p plus q, right? Modular p plus q, and we see that it is congruent to 8p squared p cubed, And this is very good because now we know that p plus q is divisible by 8 pq. But we've noticed that for this divisibility problem, we have GCD PQ they are co-prime, and we think that maybe p plus q will also be co-prime with p square, and if that is the case, we can deduce that p plus q is 8 is divisible by p plus q, right? And this is very good because we can get p plus q is less than or equal to 8, and we know they are prime, so we can test and find the final result. And indeed, we know that if p and q is co-prime, p and q plus p is also co-prime, right? And this is good because we know that if q plus p is co-prime with p, then q plus p cannot divide p, and q plus p cannot divide p cubed. So p cubed and q plus p is also co-prime, and as a result we get p plus q divides 8, and this is what we are looking for. And when p plus q is divisible by 8, we can simply test the primes, and the p is not equal to q, so p plus q can be 1, 2, 4, 8, but they are greater than 1, so they cannot be 1, and the p and q cannot be both 1 because 1 is not a prime, and p does not equal to q, so pq cannot be both 2, so it cannot be 4, and the final choice left is 8. And for 8, we've got p is equal to 3 and q is equal to 5, and that's the only solution for this equation. Yeah, and that's how we use modular arithmetic to solve this problem. We find that the essence is to use modular arithmetic to derive some condition. For example, if we mod different integer, we got different conditions, and we can have some try. And finally, when we mod p plus q, we've got a very useful condition of p plus q divides 8, and which leads to the final result.